Okay, so beyond that point, we have this XFD. Let's see. Yeah, so beyond the XFD, we'll say delta M, our boundary layer thickness in terms of velocity is just equal to something that's related to the duct itself, right? Something that's related to the pipe or the duct, the geometry that's involved. So in this case, it would be the diameter over 2, right? If I kind of scroll up. The diameter over 2, if we called this thing here the diameter, half of that is going to be my boundary layer thickness, right? So it's not too complicated. So we want to use this, okay? So let's recall Reynolds number over a flat plate. Okay, and let's kind of relate it. So Reynolds is equal to rho u infinity times x over mu, where this is basically inertial forces over viscous forces. All right, in the case of flow over external plate, x continues to change, right? X will grow, and as x grows, the Reynolds number grows. In this model, what we're looking at is, I just said that beyond XFD, things are fully developed. They stop changing. So that means the velocity profile stops changing, the shear stress profile stops changing. The shear stress itself stops changing. So how could it be that then I'm going to model this Reynolds number in terms of something that's changing, x, when nothing else is changing? Right? The Reynolds number as a measure of inertial over viscous stops being a good representation. So what ends up happening is instead of using this definition of Reynolds number, we actually change the definition of Reynolds. So for internal flow, instead of representing in terms of x, we typically represent it in terms of some characteristic dimension. So we would say RE in terms of DH, which is our hydraulic diameter. I'll give you the definition for that in a second, is going to be equal to rho u bar, right? So not u infinity, but the average velocity u bar times dh over mu. So now, if I kind of say, well, in this model up here, that entry length is maybe a small part of my overall length of the pipe. It's a better measure for me to describe things in terms of dH because that's a better representation of the important boundary layer thickness, right? It's not related to x, it's more related to the geometry itself. So as long as I can kind of capture what the geometric importance is dH, that's going to give me a better representation of the heat transfer, of the shear stress in the system, right? So I'm going to express it this way. I just have to compute what dH is. So dH, the hydraulic diameter, if you've taken fluids, you probably remember this. dH is usually defined as 4 times AC over the perimeter, right? AC is your cross-sectional area that's available for flow. So pi d squared over 4. Perimeter would be the wetted perimeter. All right, so let's write that out. This is the wetted perimeter. This is cross-sectional area. Okay, wetted perimeter, like let's say you have some odd shape, that's going to be everything that's in contact with the fluid. Okay, so this is how we compute Reynolds number. Let's see. One other thing I want to give you, so I use this U bar, right? This definition up here, this guy here. So U bar is, there's a kind of formal definition that goes along with that. You can just think of it as the average velocity, but if you want to evaluate it, and somehow you have like the velocity profile available, you can take the area integral. So the integral over the cross-sectional area of the velocity U with respect to differential area, right? So think you have some velocity profile in a duct, you just sort of integrate over that and get your average velocity. Let's see, one other thing here. Yeah, normally you can compute that in a more straightforward way by saying U bar is equal to the volumetric flow rate, V dot, over the cross-sectional area. Right? Or if you have mass flow available, it's M dot over rho density times the cross-sectional area. Right? So sometimes you'll know the volumetric or the mass flow rates. You have a pump or something, you know the speed. You can compute V dot. But those will give you the average fluid velocity. Okay. All right. So we have now this kind of understanding of Reynolds number in terms of dH instead of in terms of x. So for internal flow, we're going to represent the Reynolds number in terms of the sort of characteristic geometry being dH. Another thing you might want to do is be able to predict the hydrodynamic entry length. All right? This is going to tell us how important that entry region is for the overall behavior of the system. So let's go back to our boundary layer model. And we're going to do this again for the momentum boundary layer. We'll get to the thermal, I think, next time. So delta M for laminar flow. This is our boundary layer model for laminar flow over a flat plate. So we would say, like, this is approximately equal to the 2 times the square root of the viscosity times time. But this goes back to our analog for conduction in a semi-infinite plane wall. Right? And then we said for flow over a flat plate or flow over some coordinate system, we can replace time with x over the velocity. So we'll say this is actually 2 square root of viscosity, excuse me, times position x over the mean velocity um. So I guess I call it um here, same as u bar. Okay, so what we want to do is we're trying to solve for the layers merge. So when the layers merge, the boundary layers merge, we know something about delta M, right? We know delta M is d over 2. We also know that we're calling x at the point at which they merge x critical. So we can rewrite this, or sorry, not x critical, x FD H in this case. So we can rewrite this in terms of that, sorry, and say, okay, this is approximately now 2 times the square root of viscosity times x FD H over um. And then we just have to solve this for x FD. Right? This is what we're trying to get with the hydrodynamic entry length. So x FD H now is approximately equal to, just solving this, doing algebra. So this is, let's see, we introduce, D. So we're going to call this the hydraulic diameter DH. So this is DH squared over, it turns out to be 16 because there's a bunch of 2's that multiply together. Then times um times rho over mu, right? So this is actually the same thing as saying x FD H is approximately equal to Reynolds number in terms of DH times DH over 16, right? So kind of interesting. So we just use our definition of when we know the boundary layers are going to come together at this DH over 2. And we solve the equation algebraically, and we say approximately this is about how long it's going to take distance-wise for flow to fully merge. Okay? So what you're going to want to do with this is eventually say, how does that XFD compare to the overall length that I'm modeling? So if, let's say, XFD is 0.1, and you're modeling a length of 100, you might say, well, I don't even care about the entry region, right? I know things are changing there, but I don't care. It's not important. If it's 0.1 and your total length is 0.11, then it's important, right? Then you have to kind of take it into account. So this is how you predict the entry. One last thing I want to say is we've defined things in terms of this Reynolds critical, Right, so for Reynolds critical, if it's in terms of x, normally that's about 5e to the fifth. If we're defining now in terms of like this hydraulic diameter, d sub h, so it's no longer a definition in terms of x, but in terms of d sub h, it's a different critical number, right? It's a different Reynolds critical. So RE crit in terms of d sub h is often about 2300. So again, from fluids, you probably recognize that. So what this is saying, and we'll get to this a little bit more detail next time, is if flow comes in and you compute the Reynolds number of the flow coming in terms of DH, and it's above 2300, it'll be turbulent. Otherwise, it's going to be laminar. Okay. All right. Thanks, everyone.